Hello students, in last lecture we have seen the various current gain components and the diagram for the flux component, minority carrier distribution and the current gain or various current densities in the NPN transistor. Now in this lecture we will see the actual derivation for various current gain factors. So in order to build a good transistor, one has to determine the various transistor current components and the current gain factors in terms of electrical and geometrical parameters. So we have seen the common base current gain alpha as alpha is equal to, in terms of the current gain, this common base current gain in terms of current densities is given by JNE by JNE plus JP into JNC by JNE into JNE plus JP upon JNE plus JR plus JP. So this was our equation number 4a, and this alpha is again can be written as alpha is equal to gamma into alpha t into delta. So this is equation number 4b. So these factors which are given in this equation 4b can be defined as gamma is equal to JNE upon JNE plus JP, then alpha t is equal to JNC upon JNE and delta is equal to JNE plus JP upon JNE plus JR plus JP. So this is equation number 5a, this is equation number 5b, and this is equation number 5c. So this equation number 5a is nothing but the emitter injection efficiency factor. Equation number 5b is nothing but base transport factor, and this equation number 5c is nothing but recombination factor. So we have to see what are these factors in detail. That is, first we will see the emitter injection efficiency factor or the derivation for the emitter injection efficiency factor. So first point is emitter injection efficiency factor. So, if we initially consider the emitter injection efficiency from this equation number 5a, then one may write this equation number 5a as gamma is equal to 1 upon 1 plus Jp by Jne. So, this is next equation number 6. We derive the minority carrier distribution functions for the forward active mode, and if we note the Jne is negative in x direction, then we may write Jp as Jp is equal to minus E into dB minus E into dE into d by d of Jp is equal to minus E into d of delta P of x dash by dx dash. So, this is at x dash is equal to 0. So, this is next equation number 7a, and similarly the value of Jne as Jne is equal to minus E into dB into d by dx of delta NB of x, delta NB of x. At x is equal to 0. So, this is equation number 7b, where delta P of x dash is nothing but excess hole concentration in the emitter. This is the excess hole concentration in the emitter, and delta NB of x is nothing but the excess electron concentration in the base. So, taking appropriate derivative of delta P of x dash and delta NB of x, so we obtain the value of Jp and Jne as Jp is equal to E into dE into PeO upon Le into exponential of EVB upon KT minus 1 into 1/10 hyperbolic of XC upon LB. So this is next equation number 8a, and JNE is equal to E into dB into NBO upon LB into 1/sin hyperbolic of XB upon LB plus exponential of E into VB by KT minus 1 upon 10 hyperbolic of XB upon LB. So this is equation number 8b. If we assume base emitter junction is sufficiently forward biased so that this VB will be greater than KT by E, then the factor exponential of E VB by KT becomes greater than 1. So as this factor becomes, this exponential factor becomes greater than 1, then we get exponential of E VB by KT upon 10 hyperbolic of XB by LB which becomes greater than 1/sin hyperbolic of XB upon LB. Here we have used the different notations, that is XB is the base width, LB is the diffusion length of carriers in the base. Then here we have used this dB, that is diffusion coefficient in the base, and dE as the diffusion coefficient in the emitter. So if the emitter injection efficiency from equation number 6 can be written as or by putting all these conditions, this emitter injection efficiency which is given by this equation number 6 can be written as gamma is equal to 1/10 1 plus PO into DE into LB upon NBO into DB into LE into tan hyperbolic of XB upon LB divided by tan hyperbolic of XE by LE. So this is equation number 9A. So if we assume all the parameters in equation number 9A except PO and NBO are fixed, then in order to make this gamma which is in order to make gamma nearly equal to 1, then we must have this PO is less than NBO. If one has to achieve this gamma nearly equal to 1, then PO must be less than NBO. Then we may define this PO and NBO as PO is equal to Ni square upon Ne and NBO is equal to Ni square upon NB. Here Ni is the intrinsic carrier concentration, while Ne and Nb are the impurity doping concentration in the emitter and base. The condition that when this PO is less than NBO, and if we have to achieve this condition, that is PO is less than NBO, one must, or as this PO is equal to Ni square upon Ne and NBO is equal to Ni square upon NB, then we must have the NB is less than Ne. That is, impurity doping concentration in the base must be less than that of the impurity concentration in the emitter. So this condition means that many more electrons from the N-type emitter than the holes from P-type base will be injected across the base emitter space charge region. If both, that is XB is less than LB and if the XE is less than Ne, XE is less than LE, then the emitter injection efficiency gamma becomes gamma is equal to 1 upon (1 plus NB upon Ne into by dB into xB by xe. So this is next equation number 9b. So this equation number 9b gives the emitter injection efficiency factor. Then we will see the next, that is base transport factor.